in the past when I've done these, I've actually had to go back and edit them because someone said something unbecoming. All right. So, well, first off, does anyone have any like major questions on the quiz topic or quiz questions we've had thus far? Or is everyone pretty good on those? Because that would be a good place to start if there are any questions.
No, I went back and I like understand where he got his answers.
All right,
So
cool. All right, then. Bryce, any issues with the quizzes or no?
No, most of mine were just basic math issues.
Yeah. If even our professor makes sign errors, so that's just how it happens. But yeah, all right. So then we'll start with just going over a couple of these things. So we'll just go through 1 through 8 really quickly. And then probably if I had to take a guess, the place we should spend the most time beyond this is probably the chapter 6 stuff, which is the 3 different forms of solving. Like these, identifying which of these and then when to use which method. So starting, if we just all, number 1. Verify that y of x is equal to cx plus x squared, where c is a constant, and y of x is equal to -1 over 4 x squared are solutions to the differential equation. All right, hopefully we get a lot of these on the test because these are relatively simple. We simply, well, we have to verify that they're solutions. All right, well, there's a pretty easy way to do this. So in the actual diffie itself, we have to identify that the only thing we need to sub in here is y prime. And we were given 2 y's, so we just take the derivative of y of x is equal to cx plus x squared, and we also take the derivative of y of x is equal to -1/4 x squared. Once you have that, because this is technically a 2-part problem, it doesn't say it explicitly, but it is 2 separate questions. So our actual diffie is simply y is equal to x. Now we could leave it as y prime or write dy dx, whatever you prefer. I prefer the dy dx, honestly, but that's just how it goes. So starting off, we'll start with this, which is -1/4 x squared. So we just take the derivative of that. So if y prime is equal to -1/2 x, when you take the derivative of that. So in order to confirm it's a solution, we plug that in to the original diffie wherever y prime appears. So now we would have y is equal to x times -1/2 x plus -1/2 x squared. Starting to think this isn't going to be a solution. Well, we'll find out, won't we?
I think I remember on this test PDF, there was some discrepancies between this and the answer key. Like the letters were different. Like for the first one, it was cx plus c squared, whereas on the original one, it was different.
Although I started with the -1/4 one anyways, but yeah, it does. I just flipped over to it and it looks like there is something messed up about it with that one. But just looking at
that goes on. That's multiple ones on there, if I recall.
Yeah, that's a little weird. Yeah, because looking at this like is y is equal to. Oh wait, never mind. I just messed up. I just realized what I did. All right, I have to explain. So never mind. I think we have this. I just fundamentally missed that. So this gives us y and y prime. So we have to sub it into both sides. That's why I was making a little bit of an error. So instead, if we start with y of x is equal to this, that means y here becomes -1/4 x squared, and every y prime becomes the derivative of this, and then you simplify it down. So now if we have -1/4 x squared on the left-hand side is equal to negative 1/2 x squared plus 1/4 x squared. And that should become negative 1/4 x squared, yeah. So that is in fact a verified solution when doing this part. Now, as you said, if it's gets a little messed up if he has a discrepancy here. So we'll see here what he wanted us to do.
So is it x? Are we going to use x squared or are we going to do c squared?
It looks like he wants us to use c squared. Yeah. Which is a little weird.
Just a little.
Yeah, either way, why not? So now we have the left-hand side of the diffie equaling cx plus c squared is equal to x times the derivative of this, which is just going to be c, because a c squared is still a constant, drops to 0, even though it's got a squared on it.
Mm-hmm.
Next time c plus c squared. What do you know? It's the same thing. Works out to be, so it's going to be cx plus c squared on the left is equal to x times c, which is cx plus c squared on the right. Therefore, it is a verified solution to the differential equation given. Yay. So that's how to do those. Now, obviously, this one was a little confusing because he obviously mismatched and put an x where it shouldn't be. But otherwise, problems like this are they're mostly gimmies at the end of the day, because it's really just take derivatives and plug and chug. So hopefully we get a couple of those. This one's a little more interesting because we have to verify that this is defined implicitly by this. So when I saw this originally, I'm like, oh, this is a little confusing, but I think I get it now. So verify that the function y of x defined implicitly by the equation y to the 5th plus e to the negative 2x plus 5y is equal to 100 is the solution of the differential equation given below. So all we have to do, this is basically the same question as above, just worded differently. It gives us a differential equation and it gives us a proposed solution, and we simply have to verify that the proposed solution is in fact correct. So we have our diffie of dy dx is equal to 2e negative 2x over y to the 4th plus 1. And we simply have to take the derivative of the left-hand side. Yeah, no, wrong. We have to take the derivative of the function it gave us, which is y to the 5th plus e to the negative 2x plus 5y is equal to 100. So this one's a little tricky because it actually just, since it is just dy on the left-hand side, it means that the implicit differentiation that we're about to do should result in 2e minus 2x over y to the 4th plus 1. So it should be the same as that. So let's see. Okay, so I guess if I want to get this to look like that, first thing I would do is isolate x and y. So we have y to the 5th plus 5y on one side is equal to negative e to the negative 2x plus 100 on the right-hand side. And then if we take the derivatives of both sides with respect to x, we'll end up with a couple dy dx's sticking around. So on the left-hand side, it's going to spit out dy dx times y to the 4th. Yeah, times 5y to the 4th. 5y to the 4th plus 5, which means we can also take out a 5 out of that, which is probably going to be, can we? Oh, we could, but I'm going to leave it as that for now. It's equal to 2e to the negative 2x. 100 drops out because it's a constant. Obviously, we divide this across, it would be dy dx is equal to 2e negative 2x over 5y to the fourth plus 5. Does anyone know what to do to get rid of those 5s in the denominator? Let's see. Wait, what?
Where'd the 10 come from?
It's in the, this is another one of the problems that he mismatched. It's a,
Interesting. Even so, he does just drop a, oh wait, yeah, you're right. Yeah. So the 5 just drops out naturally.
well,
And
the
it-
5 is supposed to,
Yeah,
it goes
it
in the
reduces.
denominator and then it's,
Yeah.
yeah, 10 over 5.
Yeah, okay.
Oh, okay.
Yeah, I see it now. Yeah, so we did it correctly. If we had the right problem, we would have been fine. All right, yeah, so like this question, as I said earlier, is essentially the same thing you're doing up here. It's just a little different. Because up here, like the diffq is a little different because the dy dx's are over here. But if it's ever just a dy dx on one side, you simply have to take the derivative of the function it gives you and plug it. And if it's the same as the right, then you're good. But it's still the same thing. So we did that one correctly, which is fun. Coolio. So these two are pseudo gimmies, as long as you know how to do like basic implicit differentiation and such. Find constant solutions to this. Part number 3, I. So if we have dy dx is equal to ex squared times 1 minus y squared, if I remember correctly, we simply take 1 minus y squared and set it equal to 0 to find constant solutions of y. Which means we end up with y squared is equal to 1, y is equal to plus or minus 1, right? Square root of 1. So it'd have to be plus or minus.
Yes.
Yeah, so I'm pretty sure that's it for part 1 of this. And then part 2, we're gonna have to do a little bit more. Part 2, if y of x is a solution to this dE with y of 0 is equal to 2, then what is the value of y prime of 0? Given argument showing that the graph of y of x lies above the line of y equal to 1, what can you say about the monotonicity? Anyone can pronounce that better than me?
Monoticity?
Yes, there you go. We'll take that one. Monoticity of yx. So I'm pretty sure that's just a fancy word for saying it's got one solution. He definitely defines it earlier, somewhere in one of his things. So let's see, if y of x is a solution, then what is the value of y prime of 0? Thing is, we're given the diffq. So if we wanted to find y of x, we could just take the integral of this dy dx for part 3. But I'm starting to think that this part 2 doesn't have anything to do with the first question, maybe, but I'm not sure.
Could you do it by the separation thing to find?
Like to do the integral to find y of x?
Mm-hmm.
Yeah, it looks like it, because you can divide 1 minus y squared, bring it over to the left-hand side, and then divide by dx on the other, or multiply by dx on the other side. Although if I remember correctly, isn't the integral of ex squared impossible to compute?
Yeah, the solutions page has it as e to the x, not e to the x squared.
Bro, this
I was using this to study for one of the quizzes, and I just I just started like screen capping the answer document. Like I would just screen cap the question so I wouldn't see the solution and work on it.
We'll just do it like this because he has the whole question and then the solution's bolded. So we'll just do it this one from now on.
I think after this one, they're actually correct, but I could be wrong.
Well, we know that the constant solution is correct, as we stated. It's plus or minus 1. So there's that. But does anyone... So for this, as we said, we just want to do separation of variables then, and then take the integral to find y of x and then graph them and everything. Give an argument showing that the graph of y of x lies with the line y is equal to 1. Okay. So I think I know what this thing's asking for, at least this part, without having to do any real math. You know, y of x lies with the line y of 1. Well, we know that the constant solution curve y equals 1 is a solution. Therefore, the other graph y of x, which is also a solution, can never touch y is equal to 1 because it violates that rule of the monotonicity thing that it's you can't break that rule, otherwise it's not actually a solution. So that's what it's asking about that second part, if I had to shoot a guess.
Yeah, it's I think it's asking like you plug in like the 2 into the y.
Yeah. Yeah, if you do y prime of 0, which we have, you plug in 0, it just evaluates to -3. And then he has a big long-winded thing about the existence uniqueness theorem, which is what I was trying to remember the name of. So yes, 2 different solution curves do not meet. So this is like a big theory thing. So this is something that I feel like we're probably going to want to know how to write down, because it looks like on his tests he likes to have like theory stuff as well as just understanding how to do math.
Yay.
Although it looks like we don't actually even have to do implicit stuff here. We could, I mean, separation of variables here. We could if we wanted to actually explicitly solve for y of x, but it doesn't look like we need to. Either way, you said that after this, these are fine. Like these are all the
Yeah,
all right,
at least
good.
4 is.
At least 4. All right, that's fine. Find all the solutions for the function 2 dy dx minus x times dy dx minus 1 over 1 plus x squared is equal to 0. Well, the first thing I'd want to do is pull out the dy dx's to try and isolate that, if I had to take a shot at this. This doesn't look separable off the bat. Yeah, because they're multiplied, so. I guess I would try and expand this to start. Oh wait, no, that's gonna get wacky. That's gonna be double prime then. Oh, wait a second. Unneeded for my, yeah. So this follows the similar principle as finding constant solutions, meaning you can segment stuff and set it equal to 0. So we can do 2 dy dx minus x is equal to 0. And we can also do dy dx minus 1 over 1 plus x squared is equal to 0. Reorganize, and we get dy dx is equal to -1/2 x for one of them. Then we get dy dx is equal to 1 over 1 plus x squared for the other. We can do simple integration to get y of x, and y of x is equal to 2 separate functions. So we have, well, the integral of, what is it? -1/2 x squared is going to spit out -1/4. Yeah, -1/2 x is going to spit out -1/4 x squared. And then the integral of 1 over 1 plus x squared looks like an arctan. So it just spits out arctan. Arctan x plus c, and those other ones plus c. So that should be it. We don't have any initial values, so there's no plug. We just spit out functions with arbitrary constants. So there are 2 unique solutions. Well, there are 2 solutions to this. Any objections? Are there any questions behind how we got to the two separate solutions for this? Let's look at it. Yeah, this part.
They're both in parentheses, so they're basically two separate equations.
Yeah, it took me a sec to get to that. Initially, I was like, oh, let's just multiply it across, but then I realized that that's the worst possible thing to do. Because then you're going to get the ever feared dy or d squared dy dx squared. Unfortunate. Yeah, that'd be bad. Yeah, but as it says, you can see you just set both functions equal to 0. Therefore, you have two separate functions. Yippee-ki-yay. Easy peasy. All right, now we got to go to this one. Ooh, sketching, my favorite. Let's see what we got. This reminds me of something. This. Does this, wait, no, that's a function of y over x as the argument. I think this isn't quite, this is just x over y and it's not. Could we treat this as a chapter 6? Or should we do it a different way? No, this looks, no, never mind. This looks directly separable, right? Any arguments to just separating this?
Yeah, you
I
can
think
separate it.
Yeah, okay.
just be easier.
Yeah, definitely. So we're gonna have 1 over y dy is equal to x dx, integrate both sides with ln absolute value y plus c is equal to 1/2 x squared plus c, wacky. So we have initial values here, therefore we can solve for the arbitrary constants.
Is it 1 over y dy?
It should be 1. Yeah, no, you're right. I messed up there. It is not that. It is simply y dy is equal to x dx. So we have 1/2 y squared is equal to 1/2 x squared plus c. Reorganize this for y just cause for the explicit form. So multiply by 2 will give us y squared is equal to x squared plus 2c, which can just be redefined as c. Square root everything, just y is equal to the square root of x squared plus c. So for the IVP time, we have y is equal to 0 is equal to plus or minus 1. So we have two solution curves here. We have to consider both sides. So we do 1 and -1 is equal to the square root of c. Yeah. So it looks like c ends up being equal to +1 for both conditions, because it's going to be 1 is equal to square root c, -1 is equal to square root c, square both sides. It's always positive. Yay. And then sketch their graphs. Well, these are just square root graphs. So this is just finding the solutions, which is going to end up being, for both of them, y is equal to square root of x squared plus 1. So that's the same graph for both. So we would just draw one graph. And then the thing is, does anyone have any objections to skipping drawing the graphs?
I didn't draw the graphs when I was doing this one.
Yeah, I mean, as long as you understand what you're drawing the graph of, which is your final y is equal to, like y is equal to something x, that's what you're graphing. You're not graphing the diffie q, you're just graphing the solution, that's all. Yeah, because drawing it doesn't seem too difficult. Number 6, which is general solution of some form of some diffie q, x dy dx is equal to y plus 2x squared y. Ow. Let's see. Well, it's already pretty close to having dy dx on the side alone. So let's start by just bringing that x over. So we're gonna have dy dx equal to y plus 2x squared y all over x. Cool. Now, I can see that this looks pretty separable, because we can take y plus 2x squared y over x and rewrite it as 1 plus 2x squared over x parentheses y, which is separable. So this one will give us 1 over y dy is equal to 1 plus 2x squared x dx. Integrate both sides. We have ln absolute value y plus c is equal to complex integral. Oh, never mind, doesn't have to be complex. You can turn this into two integrals. 1 over x plus the integral of 2x instead. That's easier. And y plus c is equal to ln absolute value x plus c plus x squared plus c. I like to combine all constants to the x side, so we'll just have ln absolute value y is equal to ln absolute value x plus x squared plus c. Okay. So now it's time to finish this off. So we have ln's on both sides, so we can raise everything to e across the board to delete the ln's. So we have absolute value y is equal to what is this going to be? Absolute value x times e to the x squared times e to the c. Two e's being multiplied together is equivalent. Oh, wait, no, we don't have to write it that way. We could redefine e to the c as just a new constant, c1 or anything. So we have absolute value y is equal to absolute value x e to the x squared times c1. So there's that. So we have absolute values all over the place. We can eliminate absolute values by redefining our constant as a positive or a negative. And we can have a final solution of y is equal to x ex squared times the constant, or just times the constant out in the front, so c1. So it looks like a big part of this class is going to be figuring out how to get rid of absolute values. It's not something we learn that explicitly in the past, but it's definitely something that's big. Did anyone have any problems arriving at a y is equal to arbitrary constant times x times ex squared?
Oh no, that's pretty easy. And k is what happens, or like the arbitrary constant k is just what happens when anything happens to c, right? Like it's like either it's put into e or something else.
Does he use k?
Yeah.
Oh, okay. Let me go look at. Let's go look at that.
That's what I was really messing with.
Yeah. So he uses k, but you could, like, when it comes to defining constants, you could technically make that whatever you want, as long as it's not a variable understood to be something else. So yeah, look, so he eliminates the absolute value by defining k as a plus or minus of the original constant. So you could make that a capital A if you wanted, but yeah, so if he did k is equal to e to the c, then your final solution would be y is equal to plus or minus k x e to the x squared. But then you can see you can simplify that further by taking that plus or minus and dragging it into the definition of your arbitrary constant. And that's what he did to make it so you didn't have to have those plus or minus out in the front of the right-hand side. So when it comes to like constants, unless you're given initial values, you can almost always just keep chunking them together and redefining them. As long as you make sure to, like, if you were doing this on a test and you didn't write like k is equal to the like plus or minus e to the c, you might lose points for not defining your constant, because it does in this case have a like pseudo explicit definition. It doesn't have a real number yet, but it has a function defined by an arbitrary number. So you need to know what that function is. In this case being plus or minus e to the arbitrary constant. All right. So we have this last two. So we have 7 is dy dx. It doesn't look like we've reached, actually these ones might be new forms, but up until now we haven't really done many things besides separables. I wonder if you'll give us a test breakdown.
Yeah, I think the last two are linear.
Yeah, it looks it. So we get to use my favorite integrating factor method. And we also have an initial value here, an initial value that's a little wacky because it's pi. Well, more than just pi, but even so. Yeah, so this is this fits in the form of dy over dx minus your, or plus or minus your px is equal to, is it f of x is how it's meant to be? Is that what he says for his linear? Nope, that's separable. Yeah, y prime plus p of x y plus f of x. So in this case, our p of x y is negative 2x. So u of x is equal to the e raised to the integral of negative 2x. And when it comes to integrating factor, you leave out any arbitrary constants because it doesn't matter. So u of x is equal to e to the negative x squared, right? Yes. So this is the integral of the argument. So we start with that. Next step of integrating factor is to take it and multiply it across all the sides. So by definition, on the left-hand side, we end up with the product rule of this. So we can simply write it as u of x times y. And the whole thing is the primed is equal to, in this case, going to be e to the negative x squared times e to the 2x times cosine x. Cool. So e to the negative x squared times e to the 2x is the same as adding their arguments. Yes. So it would end up being negative 2x plus, or negative x squared plus 2x for 1e, or you can leave them separate, whatever you prefer.
The solution has a different number.
Oh, my favorite. What did it do? Let's see. I see the solution looks like, wait, the solution looks like, yeah, that's gonna change it up, huh?
Just a little.
Yeah, because now it looks like the e would drop out, doesn't it? Let's see, go through it. Not quite drop out, but it's definitely less complex than the other part. Yeah, so I guess we're gonna have to look at this then. So yeah, you do your integrating factor. He defined his u of px. Px here, he got lucky with it just being negative 2. Ours was negative 2x instead. So then multiply both sides by that. And it ends up meaning, as he shows there in the third line down, that is d dx of that, which becomes product rule, is equal to cosine x. Yeah, so it did end up dropping out. Never mind, I was right, I just missed that. So the e here drops out on the right-hand side, simplifying this drastically, because then you literally just divide by e to the negative 2x, and then that flips since it's negative in the denominator, and you're done. And then you plug and chug with numbers for solving for your constant. Yeah. It is kind of annoying that that happens, but oh well. It's likely that that these tests are old and they changed them a little bit.
Yeah, I think it says 2017 on them. So
Yeah, so at some point someone went in and edited them and then obviously didn't update something. If I had to take a guess, I think that they edited this one and didn't update the solutions, because this one, some of them don't even work on this one. So there were definitely mistakes that were made on this one. Like this doesn't actually fulfill this. But yeah, let's see. So there's that. Does number 8 have different numbers? Let's check.
no, it doesn't, from what I've seen.
Beautiful. All right. Looking at 8. Is it separable? Is it linear? We gotta figure that out. We could make this linear, couldn't we? We could divide everything by x and then subtract the negative 2y over x and slap it onto the left-hand side. That's what I would do, at least to get it into the form linear. All right, let's go with that. So rewriting this into the standard form for linear, dy dx is minus negative 2y over x is equal to x cubed times sine over 2x all over x on the right hand side. If this is the case, that means our p of x is equal to negative 2 over x. Therefore, our mu of x is equal to e raised to the integral of negative 2 over x. If you integrate that, that should spit out negative 2 times ln of x, otherwise known as ln of x to the negative 2. And we're in an e here, so we can immediately delete the e and the ln across the board. Yes. And then this whole thing would spit out x negative 2, x raised to the negative 2, or 1 over x squared, whichever way you'd prefer to write it, as our integrating factor. Doing that, that then means we have 1 over x squared times y, all raised to the first derivative, is equal to the defined right-hand side, which is just x cubed sine 2x over x times x 1 over x squared. What do you know? My favorite, it's going to delete an x cubed and then just make it sine of 2x. Awesome. Integrate both sides. Left-hand side just becomes 1 over x squared y is equal to the integral of sine of 2x, which, when worked out, the integral of sine of 2x is negative 2 cosine 2x plus c. We don't have a IVP here, so we're just going to have arbitrary constants in the solution. So this should be y is equal to x squared, or negative 2x squared cosine 2x plus c. I done goofed there. It's -1 over 2x squared cosine 2x plus c. Let's peek at this. Oh, yeah, mismatched my parentheses there. It is y is equal to x squared times the quantity c minus 1 over 2 cosine 2x. There we go. That's better. That's why I hate constants, because they suck. All right. So in terms of this practice test, they all seem relatively straightforward. Although for the most part, it really only gets up to like basic linear and doesn't touch on chapter 6 topics, which if I had to take a guess, I'm sure that these will show up considering we've air quotes completed the chapter. So I would say probably an example, like 2 of these 3 would pop up. And if I had to take a guess of which ones would pop up, I think it would be Bernoulli and it would be the first one, the first type and the third type. I don't remember doing too many second types. Although it really is a toss in the just random, depending on what he wants us to do. Is anyone opposed to doing 1 or 2 practice problems from chapter 6 that he asked us to do? I think there are only 2 or 3.
I was actually gonna go real quick because I have to study for mechanics and materials.
Ouch, that hits.
Yeah,
How's that gonna go?
probably not well.
Are you mechanical engineering?
Aerospace.
So yes. When
Alright,
do you,
so-
yeah, when does, well, good luck with that.
Yeah, because it's a test on Monday.
Ah,
Mm.
that sounds
ya.
awesome. Good luck with that.
Thank you.
Alrighty. Let's see. Let's just see. Let's see what he's assigned for chapter 6. So it looks like there's some problems.
Is that chapter 3 problems?
This is that is a little weird. That does look like chapter 3 problem. Suspiciously like chapter 3 problem. When I open chapter, I actually have chapter 3 bookmarked, the additional exercises, and 3.4 and 3.6, if I remember correctly, are the same as what he did.
Yeah.
Yeah, right there. Although looking at 3.4, 3.4 does have A through J problems.
Mm-hmm.
So we're not going to do those. We'll just look at the maybe 2 of these, I think 6 problems that he wants us to look at in 6. So I have to go find this additional exercises tab for chapter 6. Let's see. I went a little far, didn't I? Here we are. Yeah, so it looks like chapter 6, the actual word that we're looking for when describing it is substitution. So it's the 3 methods of linear substitutions. Well, linear or separable, it should always reduce into linear or separable. So he said we wants to start with 6.1. So 6.1 has parts A through C. 6.2 is a IVP singular problem. 6.3 has parts A through C. 6.4 is a singular problem with an IVP. 6.5 has parts A through C. So it alternates. I say we just do the 2 IVPs, 6.2 and 6.4.
Sounds good.
Do you have your textbook?
Yes, I'm
Okay.
looking at it right now.
All right, cool. So I don't have to take pictures or anything. All right, so 6.2, the first one, is using a substitution, solve this IVP. The problem we're looking at is dy over dx is equal to 1 plus parentheses y minus x parenthesis squared. So the parenthesis quantity is squared with IVP values of y of 0 is equal to 1 over 4. Alrighty. Well, let's open this up and try and define what's what. So looking at this, we have what looks to be type 1.
Mm-hmm. That's what I was thinking.
Yeah, standard U sub. So we have a function of x, y constant. In this case, we could just say constant 0. And our a's and b's and everything are that. So this is the general method, which is essentially down here. It becomes this separable equation. So to start with this, we define our general U sub. In this case, the U substitution should just be y minus x. And then if we do du, it should become dy dx minus 1.
Mm-hmm.
So that's that. So we have redefine, let's see.
So do you plug in the original for dy dx? Is that the...
Yeah, so here he starts with let u equal whatever. So there's that. I did this a little too U sub-y. Actually, no, I did it exactly the same way he did it. So it ends up becoming, yeah, the same thing. Yeah, so we define our u. In this case, u is equal to y minus x. Then we do the derivative of both on each side. So normally when we do u sub, we just write du is equal to. But in this case, we have to write du over dx is equal to start. So then it becomes du over dx is equal to dy over dx minus 1. Which, as you can see in his notes right around here, we did this part, we just did this, and we should get a plus b times dy dx. Well, our a's and b's are 1s. The only thing that's a little wacky is the sign. So that's exactly what we did end up getting. We got dy dx minus 1. So that's that. So then what we do, I get it. So now we take dy dx, which is the original equation, and plug it in to our new du dx equation where dy dx was. So that becomes du over dx is equal to 1 plus
you do u in there besides y minus x, or do you do...
Yeah, they just do, it looks like they just reduced it down. Since we did say let u equal to, so we just do u squared.
Okay.
So it's going to be du dx equal to 1 plus u squared. Cool.
Shouldn't you do minus 1 as well on the end?
Should it?
Like 1 plus u squared equals minus, or 1 plus u squared minus 1, and then the 1's cancel out.
I don't know if it does. Because here, let's look at this. So
Considering a is like our negative 1.
yeah. Yeah, I think you're right there. I'm trying to see why the A comes out again. Because we have our f of u times b, which is just 1, and then a is negative 1. Du dx equal to a plus b f of u. Yeah, so it should be negative 1, so they should cancel. Yeah. So then, as you said, you pull out a negative 1 on top of that. The positive and negatives cancel, and you simply have du dx is equal to u squared. You kind of had a cutout there, but even so, if we then do the derivative of both sides of this, we should just get Oh, wait, this is separable. Never mind, I messed up on that. So it's just 1 over u squared du equal to dx, derivative of both, or integral of both sides. Over u squared, bring it up. Add 1, divide by 1. So this should be negative 1 over u
Yep.
plus c is equal to just 1 plus c. Wait, no, equal to x plus c. X plus c on the other side. And then,
Crap, I
can-
just added x out of nowhere. What am I doing?
yes, no, the x does pop up because when it's just dx, it's the integral of 1. That's why I'm a little messed up a little there. So then u, as we said, is equal to y minus x. So we plug that back in. And we have negative 1 over y minus x is equal to x plus c. I just moved all the c's together onto the right. So now, do we get to leave this implicit or no? Obviously, it'd be best to solve it explicitly, but this one looks a little tricky to do that. Let's see. Ba, ba, ba. We don't have a solutions manual for these, right?
No solutions manual. All we have is the answer.
We do have the answer for this.
Like, not. It'll get like how it's worked out, but we do get the answer.
Hmm. It looks like we had a little misstep somewhere. Is the answer available on the website link you said?
Let me find it. It's in the back of the fiscal textbook.
Oh. That's more accessible than even.
This is chapter 6. 6.2. Yeah, so the answer is y of x equals x minus 1 over x minus 4.
What was it again?
Y of x
Okay.
equals x minus 1 over x minus 4.
Okay. Interested where that 4 came from.
I'm guessing it's gonna come from the 1/4 somehow when we plug it in.
Yeah, it's got to come from somewhere. Let's see. Wait. Oh yeah, it's an IVP. I forgot about that part. Yeah, that makes sense. Okay. Yeah, so this is the same solution. Yeah, so that is correct. So somewhere there was a misstep. If I had to take a guess, it might be that we misunderstood how this AB thing works. Or we didn't get it wrong. Let's see. Were you able to rearrange our answer that in a way that made it work or no? It looks like it shouldn't be able to be rearranged.
I actually got it, I think.
So you went from -1 over y minus x equal x plus c, and you pulled it off.
Yeah, I have -1 over y minus x equals x plus c, and then from there, besides trying to solve for y and then plug in the IVP, I just plugged in 0 and 1/4 into that equation to get c.
Mm.
And then once I did that, I kind of inverse both sides. So it's besides -1 over y minus x, I just put as -y times, or negative times y minus x equals 1 over x minus 4.
All right, well, if it works, it works.
Let me see if it actually works, or I'm just crazy.
Yeah, I'll plug in the 0 and see what happens. So if we have -1 over 1 over 4 is equal to
No, my negatives get off
c.
actually.
So therefore c is equal to -4. Check that. Well, now it's sus, because if c is equal to -4, it probably is right, because that's what ended up happening in the other one. So if that's the case, and we got the correct c, then we probably are correct overall then, huh? We just are having a little trouble, or at least I am, with reorienting the equation in a way that looks pretty. And let's see, I'll try it. So if I go -1 is equal to y minus x times x minus 4, divide that, we have y minus x is equal to -1 over x minus 4. Never mind, this is looking pretty obvious. Y is equal to -1 over x minus 4 plus x. Yeah, no, we're correct. You were correct in your assumption with the manipulation of the a's. Or the a, I should say. There's only one. But yep, nope, this is right. Yeah, this stuff feels like magic, honestly. Half the time. All right. Well, it's always fun to be correct, I suppose.
Yeah, I realized, because I was trying to figure out how the heck to get that y away from the x.
Yeah.
And I realized that you could really just flip.
Yeah,
both
that's what I
sides.
I looked at it and I'm like, this is impossible, but I just refused to start it. And then upon starting it, it just works. So yeah. My problem is when I look at something like that, when I do the whole multiply across, because of my it was ingrained into me in algebra that you should like distribute stuff. And that's obviously the opposite of what you want to do here. You just want to leave them parentheses or partitioned, however you'd like to say it. All right, so that's that one. That's good that we got that one right. Let's do the other IVP then to finish up with some of these.
Which is probably a lot harder.
Yeah, 6-4 looks like it says homogeneous, and if it says homogeneous, that means it's probably a form 2, DE. And it definitely looks like it.
Yep.
I'm gonna scroll down and see what his rule is for homogeneous. This one actually is also just U. It looks like it. So he's got a general solution form here. So we'll try and follow this the best we can. So 6.4, the equation we're looking at is dy dx is equal to x minus y over x plus y with an initial value of y of 0 is equal to 3. All right, this is a homogeneous, so second form, first order differential. So to start, we substitute. Now the question is, what the heck are we substituting for? It says, like, the simplest case is y over x as your function definition.
I think my friend actually sent me this problem asking for help on it, and we hadn't learned this at the time yet, and I remember her not being able to get this.
Yeah, we'll figure it out somehow, huh? Supposedly.
Hopefully.
It looks a little absurd. But let me just confirm something.
The
Yeah.
answer is not pretty.
What does it look like?
It has a square root in it and stuff. It's just, it's fun. It's gonna be great.
Square roots. All right. Now the tricky thing is figuring out what to do the first u sub of.
Yeah, because you can't pull anything out of that.
Yeah. The best you could do is make it into 1 over x plus y times x minus y, but that doesn't do much for you. Because neither of them are a function of just y, so you can't just make it regular linear, so that's not a go. So this is going to be a fun one, huh? If this shows up on the test, I'm going to freak out. Huh. Did he? Here, let's look at this thing. So this is pretty absurd. He did an example. This one looks pretty absurd. But the thing is, he just reduces it to where there actually is y over x as arguments on one side. Could we multiply by something then?
Could you like do a 1 over x or something?
Let's see. So he takes from this and he pulls out an x squared on both. So so he's just arbitrarily saying if you put a 1 over x squared on denominator and numerator, it's 0, so you can do it without manipulating the left. And in doing so, he produces y over x's arbitrarily. So
we do the same thing with our problem.
So do you want to do it with x or y's? Because if we do it with, if we make it u is equal to x over y, we can say x minus y times 1 over y and produce xy minus 1 over x over y plus 1. Or do you want to do it with x's? Theoretically, it doesn't matter.
You choose.
All right, well, I'm just going to make it so we have a negative and positive 1 instead, just because. So in that case, that means we would say dy over dx is equal to 1 over y times x minus y over 1 over y times x plus y. That simplifies to x over y minus 1 over x over y plus 1. Okay, that's that. Now we have x over y arguments. So that's what we're looking for. We're looking for elements that are x over y. In doing so, we can now say u is equal to x over y. Therefore, we can rewrite this as dy over dx is equal to u minus 1 over u plus 1. Funny. Does he make us take the derivative of u anywhere? Take that. Bop, bop, bop. The hell is this? All right, so he lets u equal to yx in this instance. If it's x over y, it just flips stuff about. Oh, ew, this product rule. Why?
This actually follows pretty similar to one of his problems.
Which one was it?
Dy over dx equals 3y minus x over 3x minus y.
This one?
No, not that one. The one below it.
I mean, yeah, it basically is the same problem, just with a coefficient somewhere.
That's weird. I have him worked out that one, but not the one above it. Oh, there you go.
Is this it? Yeah. He has two PDFs for some reason, so.
Oh yeah, because he like updated the other one.
Yeah, so, all right, well, if he did it this way, then yeah. So did he define? Yeah, so it looks like he always targets it to do y over x instead of x over y.
I think it makes the u easier.
Yeah, it does, because otherwise you end up with y is equal to x over u. So we might want to flip it instead, just to do that. Because it works, yes, but it's annoying. And it's unfortunate. So if we flip it the other way, then we instead get dy dx is equal to 1 minus y over x over 1 plus y over x instead. You sub that, you get dy dx is equal to 1 minus u over 1 plus u instead. If you do it that way, then you get that left-hand side, which ends up being a product rule. Yeah, it looks like it always ends up as that product rule, where it's u plus x du dx on the left-hand side in place of the dy dx is equal to our, in this case, looks like we probably will end up doing partial fraction decomposition stuff, as he did here, which
My
is
favorite.
yeah, not the best, huh? All right, so there's that. So he goes, what did this man do? Okay, I see. So he reorganized to get du dx alone. So then we have du dx is equal to Oh wait, no, that's because this is separable. Okay, well, his first step for his separation is doing 1 minus u, or our first step is going to be 1 minus u, 1 plus u, minus u, and then we're going to have to do the whole combine thing. How the heck did he do that? He went from 3u minus 1 over 3 minus u, and then combined it into one term with a u squared.
He multiplied u by 3 minus u on top and bottom, and then put together.
Yeah, that would do it. So did that convert it into multiplying them, or did he just... Wait, no, that's not what happened. I see it, yeah. X du dx is equal to 1 minus u times 1 plus u all over 1 plus u. That will spit out 1 minus u plus, or I should say minus u squared. Right, all over 1 plus u. Did you end up with u squared or minus u squared minus 2u plus 1? Or did the central term cancel?
1 minus 2u plus u squared over 1 plus u.
Like you have 3 terms, right? In the top?
Yeah.
Yeah, okay, that's the same then. I just reorganized with the highest
Yeah.
thing first. So negative u squared minus 2u plus 1 over 1 plus u is equal to x du dx. Well, time for the mystical magic of separating it and then doing partial fraction decomposition, theoretically. Separating here is as simple, I say simple, as dividing, we'll multiply dx to the left-hand side, right-hand side, divide the u, big U chunk to the other side, then divide the x. So we will have 1 plus u over negative u squared minus 2u plus 1 du is equal to 1 over x dx. Right. Now, ooh, wait, does this might be u subbable actually. We might not have to do partial fraction, right?
Ooh.
I say u subbable, but it's already u, but it should be very similar, right? It looks like we might not have to do it. So now we take the integral on both sides. I'm going to leave the first one as is for now and just say ln absolute value of x plus c. Cool. That's done. Now over here, instead of saying u, I'm just going to define k is equal to negative u squared minus 2u plus 1. dk is equal to negative 2u minus 2, which means I can say dk is equal to negative 2. Yeah, this way works. Negative 2 times u plus 1. U plus 1 looks suspiciously like the numerator. I say suspiciously, but it literally is. So then I do some magic somewhere. That's all du. So now that's du. That's good. So that means we have a -2 out to the front of this integral with a 1 in the numerator over k dk. I think of Donkey Kong every time I say it. All right. That is another ln. So we have -2 ln absolute value of k plus c. We could do some magic here and make this ln absolute value of k to the -2 plus c, just because, is equal to ln absolute value of x plus c. Okay, this looks pretty e-able, so I'll just e both sides. Delete, delete. We have absolute value of k minus 2 plus c is equal to absolute value of x plus c. I'll just make this. See, it occurs to me that we have to go backwards 2 substitutions now. Ew.
Yeah, that's fun. It's great.
What the hell was you even originally? I don't.
Y over x.
All right, let's get it. If u is equal to y over x and k is equal to negative u squared minus 2u plus 1, that means k is equal to negative y over x squared minus 2y over x plus 1, and k to the -2. Yeah, yeah.
If he puts this on the test, I will drop and take it over the summer. It's fine.
This is gonna be a fun time. All right, magic. Yeah, it's time for some magic. Then we got to take the k and put it back. So now we got to do. I'm gonna arbitrarily define the constant to delete these absolute value bars. So I'm gonna say fucking b or something. B is equal to plus or minus c. Okay, get rid of these absolute value bars. So now we have k to the -2 is equal to x plus b. Cool. Now, I don't want to do the square root of k. I don't want it. I mean, I don't want to square k. So I'm gonna try my best to not do that. But I don't think I get that luxury. So yeah. All right. Yeah, I don't think I get to do that. Yeah, all right. I'll just plug everything in. I'll just do it. Why not? So, big parenthesis, negative parenthesis, y over x, parenthesis squared, minus parenthesis, y over x, parenthesis, plus 1, parenthesis, squared is equal to x plus b, where b is arbitrary constant. Yeah, this sucks. You said the answer looks ugly?
It's y of x equals -x plus the square root of 2x squared plus 9.
Okay.
Yeah.
Well, I'm gonna take a page from your book on the last problem and just start shoving in the substitution and just see if it rearranges and looks pretty. That's basically as far as I'm gonna stick with that. 0 is equal to 3. All right, well, if that's the case, that means I could say that this is equal to 1 over big parenthesis, negative parenthesis 3 over, oh God, no, I can't. There's x's in every denominator. This is unacceptable. I'm gonna say that this is impossible and go and move on. I'm gonna shoot him an email about that. I think that'd be a good example to go over in class.
Yeah, if he could just
So
like
I'm gonna take a
send
note.
me a solution on this problem, that'd be
I'm
great.
gonna take a note for 6-4 to bring up tomorrow morning. or
It'll take him
after
the whole
class.
class period to do it.
No, that's why I'll bring it up afterwards, or I'll just shoot him an email, because it's a little ridiculous. There's got to be some simple mistake or something, or not, or it could just be horrible. It could really be either way.
It'll be like at the very beginning, we just missed something so simple, and then the entire problem just works fine.
That's how math works sometimes. All right. So we did those, and there is this, but this one doesn't actually. This is just like a slightly different version of the original type. And in my opinion, I think the hardest of these from what we've seen is the homogeneous, because we just tried it and got our shit rocked by it. So that's how that happens sometimes. So we went through the practice test. So we basically have everything through chapter 5 down pat. Chapter 6, relatively decent. Yeah. Assuming he has relatively acceptable questions on the exam. Chapter 9 is slope fields. I don't even think it'll show up, but if it did, we don't know enough about it yet to quite do any review for it. So that's that. So we're basically ready to drop for today.
Yeah.
So that's good, I suppose. So I always post these on YouTube for anyone who didn't get to show up. If you have any objections, make them heard.
I'm good.
No one really cares about that. It gets like 10 views. There was one actually, I posted it once, there were like 70 people who watched it, and I'm like, why would you do that?
Why would you torture yourself?
It gets, no, there are literally some like on my YouTube channel, the only things posted are those like review session things. And there's like a 2.5 hour one. And I looked at my YouTube analytics and one person watched the whole thing through, like straight through. And I'm like,
Amazing.
I don't think that's amazing. I think they're like the dumbest people in the world. Why would you do that? That's a horrible decision made by someone who obviously has nothing else to do. Because that was just disappointing. Stop the screen share. Where's the
Well, thank
recording?
you.